Hello physical science students, welcome to video number 2, which is called Detecting Radioactivity. When it's ready, here we go. Just to recap our understanding of the atom, here's a picture of an atom, not a bad one, we can see, and a couple of things will pop up here that you can read. And so what are we saying? Well, we're saying that the nucleus contains the proton. This is what the proton is. It's positively charged. We have the neutron, which is a nucleon that has no charge. What do we mean by the term nucleon? A nucleon is the collective name for particles found in the nucleus, and the nucleus is the solid center of the atom. Most of the mass of the atom is concentrated in the nucleus, and then lastly we have these guys, the electrons whizzing around, and the electron is the negatively charged particle found orbiting around the nucleus. And that's our understanding in physical science of an atom. Now, how do we detect nuclear radiation or radioactivity? There's a whole lot of different ways of detecting it. Fluorescence, which is where you get light emitted because something's absorbing radioactivity, and the byproduct of it is light is given off, which is a form of radiation. Photographic plates, which was one of the earliest methods of detecting radiation, nuclear radiation or radioactivity. An electroscope, which we don't have one way, a Geiger-Müller counter, cloud chambers and bubble chambers and spark chambers. Now there's all those techniques plus others, of course, but in physical science we're only going to look at the Geiger-Müller counters and the cloud chambers, and by that we're going to also hint at bubble chambers. Now firstly, what is a cloud chamber? Cloud chamber is just one way of seeing evidence of radiation or nuclear radiation or radioactivity. It's a fairly simple device, but it's temperamental. If I can remember, I'll pull out the physical science one that we have, and basically it looks like this. You have a chamber in which there's usually a sponge, and you sit some dry ice on it, and dry ice being very cold makes the whole inside of the chamber cold, and you soak the chamber. Usually there's a felt, but sometimes on this sponge you soak it in alcohol, pure alcohol, not something like Jim Beam or anything like that. I don't think that would actually work. And because it's super cold, this atmosphere in here becomes what's called supersaturated in alcohol vapor. And so you can't actually see it, but it's carrying as much alcohol in suspension as it possibly can. You then introduce a radioactive source in here, and when that radioactive source decays and fires off a particle out into this supersaturated alcohol vapor cloud thing, it makes clouds, little alcohol clouds, and very similar to what happens like with vapor trails from jets. Looks very similar. You just see this little split of clouds going across, and that's evidence of where a particle has gone through, because to make those clouds it's got to be ionizing, and so it goes ripping through and makes these clouds. I think on the OneNote I'll be putting some videos of cloud chambers for you to see, much better than we could actually do with our tiny little one that we have at school. And this is an example of a bubble chamber, where instead of having a supersaturated container with vapor, they have a container full of a very pure, in this case very pure water, but they could use other substances, liquids as well, and I think they do. And what happens is the particle goes in and it forms bubbles. These are very small amount of bubbles, and you can see that the patterns here are quite some are all over the place, some start from nowhere and disappear, and this is because this is a bubble chamber from a particle collider or a particle accelerator, and so lots of atomic interactions occurring. It's like here's a particle flying through here, creating a bubble trail, then it interacts or it decays, and so one particle goes off, but whatever it decayed into goes also into that. So weird and wonderful physics is happening in these sorts of things. but that's what they look like. We unfortunately won't see anything like that. But we'll put a video on the OneNote for you. Now, how does the Geiger counter work? Poor old Muller usually gets left out of the name. Two people invented it, Geiger and Muller, but they're often just called Geiger counters. Poor old Muller. But that's the way it goes. Now, we have Geiger counters at school and we'll be using them. And if we pulled one apart, we'd actually see that inside the box, a very small amount of it is actually the tube, but everything else is the electronics and the battery and the power supply and things like that. But how does the actual tube work? Well, you have a little tube which is sealed, and then it's all the air is pumped out of it, so it's at a vacuum, and then they put in a little bit of gas, a little bit of pure gas, and so it's at a very low pressure. And on the front of it you usually have a very thin foil so that particles can get through the thin foil. The outer part of the tube is usually a bit thicker. And what happens is the radiation comes in, it causes ionizing. It ionizes an atom, and if that was just a normal tube with nothing else about it, that ionization would just stop there. But what happens in the Geiger-Muller tube is they actually charge up the chamber. They make the chamber itself negative, and then they have a wire that goes through the middle which they make positive. And what the result of that is that there's a thing called an electric field between the tube and the wire, and it's a very strong electric field. And as a consequence of that is, if any atoms get ionized by radiation, they then get accelerated and move very quickly, and they actually start hitting other atoms and causing other atoms to be ionized. And it's sort of like a chain reaction where one ionization causes a whole lot of ionization, and the net result is that you get a spike. Where's my pen gone? I've lost my pen. There it is. Oh, come back here. I'm a bit out of practice. What happens is you get a current generated in this wire, and that spike in current is a recording of a radioactive event. And so on our Geiger counters, when you hear that chirping sound, that's what's happening every time there's a chirping sound. I think this explanation calls it an avalanche. An avalanche of electrons occurs, which is a pretty cool way of saying it. But that's how they work, basically, simplistically. Now, photographic plate or photographic paper is still used to detect radioactivity. And if you've ever been to the hospital, had an X-ray, or been in a lab, you may have seen people wearing things like this, and basically they're workplace radiation recorders or radioactivity recorders. And photographic paper is put in here inside a dark room and then sealed up, and there's these pads that have different thicknesses and different materials on it. And any radiation that goes through the wearer, I think I've got a picture of someone wearing one, there we are. And so any radiation that goes through that pad has to go through varying things. And these different layers, if they will help you distinguish what sort of radiation it was. And so the film or the badge is sent off once a week, once a month, and the photographic paper gets developed and gets scanned, and if anyone gets any high results, alarms go off and people have to get answers to questions about why people are getting excessive amounts of radiation in their workplace. So most people wear them wherever there's a risk involved in radioactivity. That was pretty short and sweet. In the next video we'll look at nuclear stability and the types of decay, which we've already mentioned, but we'll go into a lot more detail next time. Cheerio!